Everyone, come on in. How's everybody doing? Hopefully, y'all had a good day off.
Yeah.
All right, Logan's in the right class now, finally. Uh, you might have to get switched. I sent an email, but I haven't heard back from them, so I'm getting ready to check again, Logan. We might have to switch you back because that whoever put you in that class put you in the wrong one, and then that put you in the wrong Pearson class, and that might present some problems. So I'll send another email since I haven't heard anything yet.
Wait, so am I in the right class or not? Because it switched me on Friday back to a different one. So is that the right one?
You're actually now in the correct Canvas class, but the weird thing is the weird Pearson MyLab and Mastering is connected to a specific class. Since you did an assignment while you were in that other class, it thinks you were with that one. So I just got to move you to the other class. Uh, I'll send another email tonight to try to get on that. But if you have any problems that cause you delay, let me know and I'll give you extension because of this screw up wasn't yours.
Okay, so I won't have to do like the chapter 17 homework and conceptual again.
No, you won't
Because
have
I
to do
was
it
gonna
again.
ask.
No,
Okay,
no,
okay,
definitely not again.
thanks.
No problem. Anybody else have any questions?
Also, is the Zoom for the lab tomorrow? Is that, or I mean, is it gonna be a Zoom tomorrow?
Yes, I was hoping I might be able to drive, but my shoulder's still just pretty racked, and like I said, there's a high probability I'd screw up something if I got in a had to drive and someone pulled out in front of me or something. So,
Yeah, okay,
but the good
thanks.
news is it's another short lab. We've sort of mixed the order up. So this semester, actually, yeah, I got to double check what lab we're doing. But anyways, yeah, it shouldn't be too terribly long of a lab. Anybody else?
What
Darnisha? Yeah.
I'm sorry.
Oh, no
I'm
problem.
sorry.
I just thought you had a question. It's all good. All right. So I did post some more videos. I've got four more in the can that just need to be posted. So I've done a couple regarding linear expansion and the ideal gas law. Uh, I think that's more than enough between that and the examples in the book. You got more than enough in chapter 17. So I'm starting on chapter 18, which is called the kinetic theory of gases. And in that, we're going to basically start off with sort of you might consider it a derivation of the ideal gas law, or you might think of it as if we use the ideal gas law, it's a derivation of the average random kinetic energy of the molecules in a gas. So one of those two things are getting ready to happen. Then we'll talk about the Maxwell distribution, which is section 18.2, distribution of molecular speeds. Uh, real gases and changes of phase is really where you get the crux of your understanding of how matter behaves, and specifically a lot of the conceptual uh, ideas from this chapter come from that. But I won't be covering it as much as I'm more concerned about covering basically the calculational aspects of distribution of molecular speeds and using the derivation that we do for the average random kinetic energy. There is a section on vapor pressure and humidity. I do not require you, though in homework you can, I don't require you to calculate the relative humidity on a test. But I didn't pull it out of the homeworks because I want y'all to have that experience. And the same thing with vapor pressure. I'll just remind you that whenever you use the ideal gas law for a gas that's above a liquid, then you've got to include the vapor pressure of the liquid as part of the pressure. So that's the main reason that I'm not quote unquote skipping section 18.4 altogether. So just make sure you read section 18.4 on your own as thoroughly and as you can and try to make some sense of it. Triple points versus critical temperature, know the significance of those terms. Basically, all the bold print stuff is always fair game for basic definitions and conceptual questions. There's a temperature decrease of boiling water with altitude. That's a nice derivation that sort of everybody that completes this course should have done. So I'll definitely get you to check that out. Van der Waals equation I'm going to introduce to you. I don't know if I'm ever going to give you any problems on the actual test from it. So I'll just leave it as if we're covering it and you might be responsible for it. The mean free path and diffusion I think are really fun and they're awesome to do regarding homework stuff. But again, no, that will not be covered in the test. So I'm going to write this down in the chat. Now again, this says you will not be tested on, but that doesn't mean the homework's not available. Be tested on sections. So the sections are 18.4, 18-7, and 18-8. And I shouldn't capitalize it, I'll put lowercase. All right, so here it is. Y'all can check that out. So basically in section 18, chapter 18, you're not required to do vapor pressure and humidity, other than, like I said, making sure you understand that you do have to use the vapor pressure if you're dealing with a gas that's over top of a solid, over top of a liquid. All the other stuff, the mean free path and diffusion, I think there's one mean free path question in your homework, but I don't even think there's any diffusion in your homework. But I'm okay with those being in homework. I'm just not going to test you on them. So, any questions on that stuff? All right. Well, let me go ahead and get started. Your book always opens up with a chapter opening question. So, like this chapter has the typical speed of an air molecule at room temperature, 20 degrees Celsius, is what? And they have answers like nearly at rest, which means less than 10 kilometers per hour, on the order of 10 kilometers per hour, on the order of 100 kilometers per hour, on the order of 1,000 kilometers per hour, and nearly the speed of light. So that's a typical question that might come up, but I really want, like I said, every time you start a chapter, that chapter opening question is sort of important for you to read and have some idea what the answer is going to be in terms of you at least guessing or using what you've learned from science in the past. And then later we're going to learn a way to actually calculate it. And you can then correct your logic and then keep that new learning in mind. So definitely do that. Other than that, I'm going to go ahead and start by talking about the ideal gas law and the molecular interpretation of temperature. In other words, I'm going to do that derivation that I told you about. Your book gives you some very specific assumptions regarding kinetic theory for an ideal gas. So I'm going to read over those rather than to take the time to write them out because, as you can imagine, that's a pain in the butt. So I'm trying to remember what page it is. And because I'm using the ebook, it doesn't really matter too terribly much, but I will say read beginning of section 18-1. So this is where this is coming from. So the basic postulates for kinetic theory of an ideal gas are: one, there are a large number of molecules, capital N, each of mass, lowercase m, moving in random directions with a variety of speeds. This assumption agrees with our observation that a gas fills its container and, in the case of air on Earth, is kept from escaping only by the force of gravity. Number two, molecules are, on average, far apart from one another. That is, their average separation is greater than the diameter of each molecule. So they're saying molecules, but what we're working on here is if we're actually doing elements, elemental gases and stuff like that, then this applies for the atoms as well. So just keep that in mind, even though they're using the word molecules. Now, three, molecules are assumed to obey the laws of classical mechanics and are assumed to interact with one another only when they collide. Although molecules exert weak attractive forces on each other between collisions, the potential energy associated with these forces is small compared to their kinetic energy. And then finally, number four, collision with another molecule or the wall of the vessel are assumed to be perfectly elastic, like the collisions of perfectly elastic billiard balls covered in chapter 9. We assume the collisions are of very short duration compared to the time between collisions. Then we can ignore potential energy associated with collisions in comparing to the kinetic energy between collisions. Okay. So that's those are basically the rules that we're going by. So what I'm going to do now is I'm going to share my screen with you and start working on this derivation. And it's not too difficult, and in fact, it's kind of neat to be able to do anyways. So I think you might enjoy it. So as soon as this comes up, all right, we got it up now. So what I'm going to start off with is I am going to imagine an XYZ coordinate system. So here's my z-axis. That's my x-axis. And going into the board or into the screen is my y-axis. So I'm going to say this is x, this is y, and this is z. And you probably are wondering, why didn't we just draw the y-axis out? Well, with the x to the right and the z-axis down, I mean up, y cannot be where it is because x, y, z has to be what we call a right-handed coordinate system. And that means if I take my index finger of my right hand and point in the direction of the x-axis, the positive x-axis, which is to our right, and then I take my middle finger and point that perpendicular to the x, and then I put my thumb perpendicular to both of those, then the middle finger should represent the direction of the y-axis, and the z should represent the thumb should represent the z-axis. So for you guys, what we're looking at is that, and of course, that finger going towards you is going into the page. So that's why that is the way it is. So now let's go ahead and talk about our object. So we're going to have a container of gas, if you will. That container of gas, just for simplicity, we're going to make it like a cube. But to be honest with you, you could do this whole derivation without assuming it's a cube, and that works just fine as well. It's a little easier this way, and therefore we do it that way. Okay. So there's your box, if you will. And that box represents, like I said, the volume of gas that we're studying. What we're going to say is that this distance from here to here is L. And we're also going to say that this surface area, as well as the one opposite it, has an area A. Okay. So this one over here also has an area A, like that. Now inside of here, I'm going to imagine a bunch of little atoms moving in random directions. And these directions are not just in the XZ plane, they are in fact in the YZ plane, the YX plane, along the Y axis, along the Z axis, all sorts of stuff. And in fact, I'm going to focus on one particular atom or molecule that slams into the wall and then bounces off. And this is the one we're looking at, this little red guy right here. And this is it in the future. Okay. So what we're going to try to make use of is we're going to try to calculate the force on that wall. So the force on the wall, according to Newton's second law, is dp dt. Now, you're probably used, if you had me, you're used to me writing the summation of the forces is equal to dp dt like that. And that's technically what we're doing. But really, all we're thinking about right now is what exactly is the force acting on the particular particle, which in this case, we're assuming is like a molecule. So we're actually asking what that force is. And that's the only force. So I can equally well write it as just F is equal to dp dt. Okay. Now P, the momentum, is equal to m times v. And I don't really care too much to deal with the vectorness of it because there's going to be some principles of physics that help us sort this out quite well. So what I'm going to say is F is approximately equal to delta P delta T. But as the time interval gets really, really small, uh, but not too terribly small. Basically, there's going to be an averaging process from all the molecules such that this little delta versus differential is not going to matter. So we'll start off by calculating delta P, which equals delta mv. And I'm doing it specifically for that one particle. So initially, this particle has P initial equal to m times v sub x, and that's the x component of momentum because that's all I care about really, because as I said, we're going to deal with the other dimensions later. And this is p final for the x. And in fact, the p initial technically has to be a minus in front of it because you can see it's going in the negative x direction, and the p final is actually going in the positive x direction. And notice I did not use a different mass because obviously it's an atom or a molecule and it's not going to change because it runs into the wall. And two, I didn't put a subscript or anything on the v sub x. In other words, I used the exact same velocity. Can anybody tell me why I use the exact same x component of velocity? I will give you a hint. It's about an ideal gas. And we just finished reading four conditions about an ideal gas. Does anybody recall the proper one or the one that I'm asking about? So these collisions are elastic. And if you remember from last semester, elastic collisions mean not only is momentum conserved, which is true as long as the net force acting on the system is zero, but also the kinetic energy is conserved. So the kinetic energy before the collision for that one atom or molecule is 1/2 mvx squared. And that also has to be equal to 1/2 mvx squared at the end. So yeah, we can't subscript the velocity. So what I end up getting is mv sub x minus negative mv sub x, which gives me, in fact, 2mv sub x. And that is the change in momentum in going from that instant that it ran into the wall to the instant it left the wall. Okay. Now, we know what's happening here. These atoms and molecules are all going in random directions. So they have an x component, a y component, and a z component of velocity. But since the collisions are elastic, if this particular particle, for instance, rams into the left side, it's going to bounce off and go away with only the x component of velocity changing directions. So the magnitude is not going to change, but the fact that it was going in the negative x direction is now going in the positive x direction is going to change it. Now, if you keep watching it, there's a time will elapse where it'll go and maybe bounce off the right-hand wall and then bounce off the ceiling. When it bounces off the ceiling, the same thing's going to happen. Whatever component of velocity it had in the z-axis, for instance, was positive, and then after the collision it'll be negative, but it'll have the same magnitude. And since it doesn't affect the x component of velocity or the y component of velocity, it doesn't affect the overall velocity at all, really. It's just changing that particular component direction. And because of that, I think you can see that if you watch this one particle long enough time, I think you will reach the conclusion that the time period delta t uh, will actually be twice the distance across the side of the box parallel to x-axis. In other words, twice L. And then that'll be divided by v sub x. And basically what we're saying is that's the amount of time between one collision into the left wall and another collision in the left wall, right? Because yes, it is going to be moving to the right, and it's going to be moving maybe towards the back or towards the front and towards the top or towards the bottom, but those are not going to slow it down left and right or in and out. So, yes, Nathan.
When you were talking about the elastic collision with the wall, were you
Uh,
assuming that there was absolutely no energy transfer between the wall and the particle?
Yeah, that's part of the original assumption. Those four conditions I read was that it's an elastic collision, and since it's elastic, kinetic energy has to be conserved. So there's no way any other energy could be lost. Period.
Okay, like
Mhm.
perfectly elastic. Gotcha.
Exactly. Yep. So this time is the time between two collisions on left face. Okay. So we sort of have something we can work with right here. We can see, F is going to be dp over dt, but we're not quite where we want to really go. That being said, let's go ahead and write it out anyways, just to look at what we've gotten so far. Looks like another student just came in. Okay. So what we have so far is F is equal to approximately delta P over delta T, which we found was in fact 2m v sub x over 2L divided by v sub x. And I think you can see the 2's are going to cancel out here. And ultimately what we're going to get is m v sub x squared over L. So this is all due to one molecule. Again, we're saying molecule, but that also covers the case of an atom if necessary. And I didn't write that or very well, so I'm going to fix it because, I'm OCD and I can't help. Whoa. Probably you're thinking, well, given his handwriting, I'm pretty sure he's not all that OCD, but I try. Okay. So now that we have that, we have some idea of what molecule is going to actually be doing, what one molecule specifically is actually going to be doing. But in fact, we have N molecules. So we're going to assume, like the original assumption said, we have N molecules so that the total force, whoa, evidently I'm going to start spelling force with a V. The total force is, so now we have F is equal to, I can pull that M and that L out in front because obviously they're not going to change. All the atoms or molecules are identical is what we're saying here. So what I have is V1x squared. So that's for the first particle. Plus for the second particle, I have V2x squared plus dot 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 plus Vnx squared. So basically, what I have to do is sum up all the individual contributions from all the atoms or molecules, and I do so by doing that. Now, we do know that we can define a quantity Vx squared bar, which is really the square of, or excuse me, the mean of the square of the x components of velocity. And that's actually going to be v1x squared plus v2x squared plus dot 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 plus v n x squared. Of course, in taking an average, we just add all those up and divide by n. Now, we know that the average is going to have units of like Newton, or excuse me, meters per second squared. So if we actually want to treat it like a velocity, we ultimately have to take the square root of that number. That's going to turn out to be what we call a root mean square, and it's going to come in handy. But for right now, I'm just telling you, we are averaging the squares of the velocities, not the actual velocity. Now, if you think about that, then we actually could change the force to the total force is now equal to F. And notice the difference between the sum of the Vx's that we have here, which I say right here. This is the same as the numerator of this expression. So all I have to do now is basically write, getting the right color pen in place, is m times m over L times n, the total number of particles, times the average squared velocity in the x direction. Okay. So that's the total force on, the left face as a result of all the individual particles. But we can do better than that because we know that v squared is equal to vx squared, is equal to vx squared plus vy squared plus vz squared. And we are talking about averages here, and there's no reason for one particular direction to be more important than the other. So we expect the net average of these is such that the average of Vx squared is equal to the average of Vy squared is equal to the average of Vz squared. So in fact, we can go ahead and replace V squared, or I should say Vx squared, on average. We can replace that with just 1/3 V squared on average. So in doing that, we now have F is equal to M over L times N, the total number of particles, times the average of V squared over 3. Now, we have to figure out exactly what the pressure is. So pressure is defined to be force divided by the area perpendicular. Okay. And for our left-hand side, what we found was that the area on the left-hand side is just A, and of course, the length is just L. So the area we can actually figure out, and notice it will come in terms of the L as well. So now what I can do is I can say that the pressure is actually going to be equal to F over A. We already found out that F was M over L times N times Vx, or excuse me, times V bar squared. Sorry about that. Yeah, I did do it. Okay, sorry. I was just making sure I hadn't forgot to take off the X on the last one, but I forgot I wrote it on the same line. Let me just go ahead and kill that and just write it again. So this will be V squared bar. Now we're going to divide that by the area, which is A. And I think what you'll see is you get M times, and I forgot the factor of 3. What I'll say is I get 1/3 of M times N times V squared bar over A times L. Can anybody tell me, with regards to the diagram above, what AL is? So see the diagram of the box? Anyone?
Is it area and length?
Yeah, it's area times length. So what would that be? For that particular box, if I multiplied A times L.
Volume?
Exactly. So because we have a V here, I'm going to make it this fancy V just to remind everybody that it is technically volume. I'm going to now come up here, and this isn't the best way to do it, but I would like to keep this all on one page. So now what I'm going to do is I'm going to say P times V is equal to 1/3. And then, of course, the 1/3 also has a m times n times v squared. So I'm going to say 1/3 n times m times v squared average, which is pretty nice, but I can even do it a little fancier by replacing the mv squared with 1/2 mv squared. What's 1/2 mv squared? Anybody? What is 1/2 mv squared? It's the kinetic energy. So what I did was I multiplied by 2 and divided by 2. Multiplied by 2 to put it in front of the big N, and I divided by 2 to put in front of the mv squared. So what I have here is the kinetic energy per molecule. Okay. So that allows us to figure out something. So for starters, we know from the ideal gas law, which could be written in many ways. So remember ideal gas law. It's PV equals nRT, but in your reading of the chapter 17, hopefully you saw this as well, or hopefully you've already covered it as well. But basically, another version of the ideal gas law is, instead of using the number of moles, you can use the number of particles in, and then KBT. And from that, I think you can see that basically there's a relationship between K and R that involves basically the Avogadro's number. So this is the version I'm going to use. I already have PV equals N times K times T. So I can actually now say, by setting these two to equal to each other, I can say that 2/3 of 1/2 mv squared is equal to basically just KT. And this is from the ideal gas law. So in other words, all I did was took this asterisk right here and used it to set equal to the PV part. So if I put PV equals N KT, you see that the N's cancel out on left and right. So you end up just getting NKT canceling out with the N's, gives you KT is equal to that. And this quantity, of course, is the average kinetic energy. So what we're going to call this is just the average kinetic energy, K bar. Okay. So our ultimate result is average kinetic energy is equal to 1/2 mv squared with a bar over it, which equals 3 halves KT. And that's the result we were looking for. I will say that K is often called K sub B. It's called the Boltzmann constant, and it's 1.3807 times 10 to the negative 23rd joules per Kelvin. Okay, so this is our world famous result. The average kinetic energy, K bar, is 1/2 mv squared bar equals 3 halves KT. And what it tells us is the average translational kinetic energy of molecules in random motion in an ideal gas is directly proportional to the absolute temperature of the gas. So that was the premise that we were telling you last time when I said that the average kinetic energy of the molecules is directly proportional to the temperature. In fact, this is now our specific definition of temperature. So if you could, freeze time and walk up to someone, sister, brother, wife, stranger, whatever, doesn't matter. And in freezing time, you were able to ask every molecule and atom that's in that person's body. And you ask them, what's your average speed? What's your mass? Or what's the average of the square of your velocity and your mass? And you write that down, and you do it for the next one, and you do it for the next one, and you do it for the next one, and you do it for the next. Now this would take 10 to the 30th years or something god awful like that. So you necessarily don't have the time to do it. But in principle, if you were able to do that, then you could go ahead and make a tabulation and take each of the masses and the average velocity squared of each of the atoms or molecules, multiply that by 1/2, add them all up for all of those, and then lo and behold, all you'd have to do is multiply by 2/3 and divide by Boltzmann constant, and that would give you the temperature in Kelvin. So, any questions on that? All right, so that little blue equation in the box, or that blue box around the black equation, is the fundamental result we're getting. And of course, we've already used the ideal gas laws, but we're using the form of the ideal gas law with the Boltzmann constant, which you see in the little red box. So, anyone have any questions on that? All right, so maybe we should go ahead and consider the average kinetic energy of molecules in an ideal gas at 20 degrees Celsius. So that's going to be our first example. What is the average? And I'm going to put an extra word in here because this part is important. Average translational, that's the extra word. Kinetic energy I didn't necessarily have to make that K capitalized. What's the average kinetic energy, average translational kinetic energy of the molecules And actually, I'm not going to do 20 degrees Celsius. We'll do that later. But let's say, what's the average kinetic energy, translational kinetic energy of the molecules in an ideal gas at, let's say, 40.0 degrees Celsius. So here's our solution. What we know is the average kinetic energy is equal to 1/2 mv squared, like that. And that's equal to 3 halves KT times T. So we can say that the average kinetic energy is 3/2 times 1.3807 times 10 to the negative 23rd joules per Kelvin times, now I've got to add 40 degrees Celsius to 273.15 technically. So that's 273, that'd be 311 or 313, excuse me. 313.15 Kelvin. 273, that'd be 283, 293, 303. Yeah, 313. All right. So now we can do that calculation. I'm going to pull that out of my calculator right now. 1.5, which is what 3/2 is, times 1.3807 e to the negative 23 times and in this case I get 6.48. And then the next digit is 5, extra sig fig, and that's times 10. Oh man. Times 10 to the negative 21 joules. So not terribly high, obviously. Now, the reason I said translational, I've sort of hinted to that already, but really, if the atom or molecule is vibrating among within itself, like if it's a pair of dumbbells, that would be a molecule that has a atom on one end and a bond, and then an atom on the other end. They could actually vibrate, but that's a translational kinetic energy of each of the individual atoms. But the motion of the molecule is more or less what its center does. But the main thing is there's two axes about which that can be rotated, and those motions are rotational motions, not translational motions, so they're not counting in that V. Okay. Anybody have any questions on that answer?
No.
Nope. Okay. So let's try another one. So the opening question in the book was what is the root mean square speed? And root mean square speed is another type of average, but it's not exactly the average that you're used to doing. So in principle, what you're supposed to do to get the root mean square speed is you average the squares of the speeds. That gets you from prevents you from having the negatives that are associated with the components, like a negative x component, for instance. If you try to take an average of all the x components, you're going to ultimately just get 0. But by taking the square, that gets rid of the negative components of it, and therefore you always get a slightly bigger value. So anyways, we're asking what is the RMS speed? I should just say, what is the RMS? Which is root mean square speed of the molecules. Oops. Dang it. Of O2 and N2 in the atmosphere at 20.0 degrees Celsius. So this is directly addressing that question. So here's our solution. What we know is K bar is equal to 1/2 mv squared bar, but that's also equal to 3/2 kT. So if I just take the two last parts, what I'll see is that m V squared average is equal to 3KT, or specifically VRMS, which equals the square root of V squared bar, is equal to 3 times K times T over M with the square root taken. So we're going to take the square root of all this junk, which would be 3 times 1.3807 times 10 to the negative 23rd. It's obvious that I continue to try to write something other than 3 when I do that, but joules per Kelvin. And then the temperature for 20 degrees Celsius, that's going to be 293.15. And I just put that 15 because that's, what I'm used to writing down. Using 3 sig figs, you should at least use one extra one if you have it, but it's fine either way. Now what we've got to do is say this one will be for the N2. So the weight of a single N2 molecule is basically 28, because it's 14, and there's 2 of them. 14 times 2 is 28. So it's 28 U per molecule, basically. I won't even take the time to write that. I'll just write U. And then the conversion has to be made, and that conversion is 1.6605 times 10 to the negative 27, and that is kilograms per U. So if you look, a joule is a Newton meter. The Kelvin's obviously going to cancel out automatically, but the Newton meter would be a kilogram meter squared per second squared. If I divide that by kilogram, then I just get meters squared per second squared. And when I take the square root of meters squared per second squared, I get just meters per second. So that's what we're doing here. So I can go ahead and write this answer. I'm going to take and do a parenthesis. I'll do 3 times 1.3807. Crap. I just hit something that made my calculator go into a mode that I can't remember how to get out of. Let's see. Oh, there you go. Got it. E to the negative 23 times 293.15. And then I'm going to divide that by, and here I'm going to use parentheses again because I'm doing the multiplication in the denominator. And if I just blindly do the multiplication in the denominator, the calculator will treat that as if I divided by the first thing but multiplied by the second thing. So 1.6605 e to the negative 27. Whoa, Nelly.
Professor, are you still writing?
No, I haven't. I'm computing it at this point. Go
Okay.
ahead. All right. So I get 511.04 meters per second for that one. Obviously, we put in, this is all multiplication and division. So we put in 3 sig figs. We should get out 3 sig figs. So the answer should be 511 meters per second. Now, if you wanted to convert that to kilometers, what you're going to do is basically divide it by 1,000 to make it kilometers, and then you're going to multiply it by 3,600 to make it hours. So that's about 1,840 kilometers per hour. Any questions on that one? All right, so that's the N2. Why don't you guys give the O2 calculation a try? I will tell you that the O2, of course, has a atomic weight. Oxygen by itself has an atomic weight of 16, so O2 would have a molecular weight of 32. So you should be able to go from there. You do it, I do it, we'll see if we get the same answers. You should be trying this on your own though, so make sure you look back when you're done to get the answer, but try not to look for a little while. Okay, hopefully everybody was able to do that like me. I am now going to actually compute the result. So I'm going to take actually a quick and dirty way is take the square root of 28 because that's what I divided by in the previous version, and divide that 28 by 32, put that all under the square root, and then multiply that all times the answer, the 511 that we got. And that gave me 478.04. meters per second. Again, that's 2 extra sig figs. And again, we could divide that by 1,000 and then multiply by 3,600, which is basically just the same thing as multiplying by 3.6. And for that, we get about 1,720 kilometers per hour. So, any questions on that one? No questions? All right, so just to give you a sense of exactly what root mean square is, let me do another example. So what is the average of the integers 1, 2, 3 on up to 5, and what is the RMS of those numbers? Okay, so just to give you an idea of what this root mean square is, we'll first consider an average. The average I will call X bar. By the way, a lot of times we use these two notations to express averages. So you can either put a bar over it or you can put less than and then a greater than symbol around it. In this case, all we're going to do is we're going to take 1 plus 2, which is 3, plus 3, which is 6, plus 4, which is 10, plus 5, which is 15. And then we're going to divide it by 5, which gives us 3.0. So that's what the mean is. Now, x root mean square really is the average of each x squared and then take the square root of it. Okay, so what we're going to do is we're going to take 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared and divide that by 5 and then take the square root of all that. So 1 squared is 1, plus 2 squared, which is 4, so we're up to 5, plus 3 squared, which is 9, 9 plus 5 is 14, plus 4 squared is 16, so we're up to 14 plus 16, that should be 30, and then 25, which is 5 squared, gives me 55. 55 divided by 5 is 11, so it should be the square root of 11, which is 3.316. Okay. So that's the answers, and that's how you compute it. Anybody have any questions on that? So your book does some conceptual examples, which are pretty nice. Like for this one, it says a tank of helium is used to fill balloons. As each balloon is filled, the number of helium atoms remaining in the tank decreases. How does this affect the root mean square speed of the molecules remaining in the tank? So what you might notice is we go on the assumption that there are actually collisions between the individual particles. So less particles would suggest that you're actually going to have less collisions. And we know that the root mean square speed of those molecules, or in this case, helium atoms, would be the square root of 3 kT over m, where m is the mass of the helium atom. So it's only the temperature that actually matters, not the pressure, or the number of moles, because you see that the root mean square speed really only depends on T. If the tank remains at a constant ambient temperature, then the RMS speed would remain constant even though the pressure of helium in the tank decreases. If you've ever actually filled something, like if you've ever worked, say, at a scuba shop like I have, where you would actually fill a scuba tank, you'll notice that the tank gets hot when you fill it, and some stuff happens to the machine or the tank that it's pulling the air from as well. So the idea that you can do that without changing the temperature is pretty slim. But anyways, that's what they're shooting for here. Any questions on that? All right, your book does average speed and root mean square speed, but it does it for some very specific numbers. It does 1, 6, 4, 2, 6, 3, 2, 5, and does that. So you can get another example to look at by just checking out the book. But that basically is it. And also it tells you, if you look at that formula, the fact that the average kinetic energy is 3/2 kT would tell us that if we actually brought the temperature down to 0 Kelvin, what kinetic energy would the molecules have? So let me write a refresher here. The result we just discovered was K bar is equal to 1/2 mv squared bar, which you could also write as 1/2 mvrms squared, like that. But it's also equal to 3/2 kT. So what does the kinetic energy become as T approaches 0?
Zero.
Exactly. But quantum mechanics doesn't allow that to happen. So we find out that that's one of the ramifications of reality versus an ideal gas. In principle, an ideal gas should reach zero kinetic energy of translational motion for its atoms or molecules at 0 Kelvin. But in fact, the very idea of bringing something down to 0 Kelvin is the antithesis of the ideal gas law, because the ideal gas law holds for very specific things. Specifically, it holds when the conditions are such that the individual atoms have a negligible, or individual molecules have a negligible force between them, right? If you start to bring something small down to lower and lower temperatures, even especially approaching 0 Kelvin, the volume is going to decrease quite a bit, and therefore the atoms are going to get a lot closer together, and the molecular forces that attract one molecule to the other or one atom to the other are actually going to become large enough for it to actually condense out and become a liquid and maybe even a solid. Those are exactly the conditions where the ideal gas law fails miserably. So it's not appropriate to use it that way. But anyways, we've now talked about that. Now, it turns out that works pretty well, but in general, there is a very specific distribution of speeds. You might want to know, exactly how fast is a particular molecule going, or what's the range of molecular speeds and that sort of stuff. But in order to do that, that brings us to the Maxwell distribution. So the Maxwell distribution. Now, Maxwell is James Clerk Maxwell, which you hear occasionally mentioned on Big Bang Theory, but you'll hear it a lot this semester because James Clerk Maxwell, he held the Lucasian Professor of Mathematics at Cambridge University. That's the same position that Isaac Newton held. It's the same position that uh, Paul Dirac held. He's the person that single-handedly came up with a relativistically correct quantum mechanics equation for the quantum state. In other words, the Schrodinger equation that we came up for quantum mechanics was not consistent with special relativity. Dirac made one that was consistent with special relativity, and he published it, and people started asking him, "Hey, Mr. Dirac, Dr. Dirac, I don't think this is going to work because it has negative energies." He said, "No, the equation's right. The negative energies must point to the existence of antimatter." So he literally said, "My equation's right. I suspect there exists some matter we haven't found before because I'm so confident in my equation." And lo and behold, he turned out to be right. So so Dirac held that, as did Stephen Hawking. He was holding it right up until just before he passed away, and Witten is holding it now. So anyways, this is a very esteemed position, but that's what James Clerk Maxwell had came up with, this fancy equation. But he also is the one that we're going to be studying the majority of the semester, specifically when we get into chapter 21 through 31. All those chapters are about what we call Maxwell's equations. So Maxwell, even though he died uh, without the full appreciation of his peers, uh, he has since been vindicated. People thought he was a little bit crazy, partly because they didn't like this fancy mathematics he used to render the Maxwell equations in a state of basically a vector calculus type state, and they were very, unimpressed. But to be honest with you, he did that. He also found a mistake in the discoveries that people like Michael Faraday had made beforehand, and had to add an extra term so it'd be internally consistent. So he came up with that equation. He is also one of the first persons to ever predict exactly what the rings of Saturn were. He showed that they could not be disks and stuff like that. He obviously made up this distribution of speeds for molecules and atoms. Really, to be honest with you, before we even conclusively knew that atoms and molecules existed. In fact, we didn't really get a robust uh, proof of atoms existing until 1905, when Einstein explained Brownian motion. So literally we had no idea, but here's what Maxwell did. So what Maxwell did is, and you don't have to derive this, I don't derive it, but what we're going to do is we're going to use the Maxwell distribution of speeds called f of v, and f of v, where v is the speed, is equal to 4 pi times n, which is the total number of particles that you have, of course, and molecules or atoms mainly. And then all of that is divided by m over 2 pi kt. And all of that is raised to the 3/2 power. And then all of that is also multiplied by the square of the velocity and e raised to the negative mv squared 1/2 over kt. So one thing to note here, just like the ideal gas law, the T has to be put in Kelvin with this equation as well as the previous equation. And here as well. And here as well. So that's the Maxwell-Boltzmann distribution. And basically it means that F of V times dV is equal to the number of particles, let's say atoms are molecules, with speeds between, oops, left out another E, V and V plus dV. So whatever V you put in there, you're basically calculating how many particles have at least that much speed and all the way up to that much speed plus dV. So if you realize that's what it is, then you'll discover some other neat things. So this one's something that's super important. I'm going to box it off in red. And it has with it certain things like the integral. Oops, I should probably write this in blue. The integral from 0 to infinity, because in principle, if we ignore relativity, the maximum velocity that something could have would be infinity. So we're actually going to integrate f of v dv from 0 to infinity. And remember, f of v dv is the number of particles with a velocity between v and v plus dv. But if we allow that v to go from 0 to infinity, it would mean all of the particles. So that makes you get plain n for the answer. If we were to draw a graph of this distribution, which I'm going to do now, what we'd put down here is v, the velocity, and what we put down here is relative number of molecules. Whoa. Evidently, I cannot be bothered by writing correctly or even using the proper alphabet. So, relative number, dang it. I put that in quotation marks because you know it's atoms as well. So that's the relative number of molecules. And if we plot this, what you'll get is a side that actually looks quite steep on one side, like this, and then it'll crest over, and then it falls down a little more gradually. And there's some really important characteristic velocities associated with this. This one, which is at the peak, is VP. Then there's another one that's a little bit past that. That one is V bar. And then a little one that's bigger than that too, and that's VRMS. Okay. VP equals most probable. Speed. So given that VP is the most probable speed, can you imagine any way we might determine what VP is using this Maxwell distribution? No. Let me check my chat, see if anybody's answering there. They have not answered there yet either.
Take the derivative and set it equal to 0.
Exactly. So the most probable speed is a maxima of the f of v. So if you actually took the derivative of f of v, you should be able to set that equal to 0 and then solve for v, and that should be the v most probable. So if you do that, this is what it looks like. So we're going to say, whoa, Nelly. We're going to say use calculus to find VP. And this will be our solution. I want df of v with respect to v set equal to 0. So when we do that, you might notice, for instance, that we're taking the derivative with respect to v and really only v. So basically, we get to pull out everything out in front. I'm going to say 4 pi n m over 2 pi kt to the 3/2 power. And then all I can do is take d by dv of v squared e to the negative mv squared times 1/2 all over, kt. Like that. And then I'm going to set it equal to 0. So the reason I'm showing you that is clearly none of these terms are going to matter. Now, in taking that, I have to use the quotient rule. So now I'm going to say 2v e to the negative blah, blah, blah plus v squared. Now, the derivative of e to the x, for instance, is as e to the x. But then you got to take the derivative of the exponent. So the derivative of that exponent with respect to v is, in fact, whoa, Nelly, hate this thing always doing that. The derivative of that exponent is actually negative. Now I take the derivative of v squared, that's 2mv, but there's already a 1/2 in there, so I'm just going to say mv over kt, like that. And now e to the negative blah, blah, blah. Now, there's no way I can make e to the negative something 0. So that's not really going to be that relevant to all of this. So at this point, I now have what I need. I can divide through by the e to the negative kt, and what I'm going to get is 2v minus mv cubed over kt is equal to 0. So ultimately, we can say 2v is equal to mv cubed over kt. Obviously, one of these v's cancel out with that, and I can now solve for v. And I'd say v equals 2kt over m. And then we take the square root of that, and that should be VP. Any questions on that? So this is approximately, by the way, 1.414 times the square root of kt over m. So that's kind of a big deal. we already knew VRMS was equal to the square root of 3 KT over M, which is about equal to 1.73. Let's do our square root of 3 just to make sure. 1.732 times the square root of KT over M. And then, of course, there's V bar and VRMS. Both of those formulas quite a beast. So if you actually want to compute V bar, the way you do it is you'd say, actually, I don't want to use red. So what we're going to do is we'll say V bar is equal to the integral from 0 to infinity of V times f of V dV. And then, of course, to make it the average, you got to divide by n, because basically what we're going to get is n times the average velocity. If you carry all that out, you'll get basically 4 pi m over 2 pi kt. That got rid of that big factor of m, notice, of n, excuse me, capital N. And that becomes the integral from 0 to infinity of v cubed e to the negative mv squared 1/2 kt, like that, dv. And lo and behold, that answer turns out to be the square root of 8 over pi times kt over m, which is approximately 1.60 times the square root of kt over m. So this is a good practice for you to try. You can just look this up in a table, or you can use integration by parts. Integration by parts, in case you're a little rusty on that, basically says the integral of u dv equals uv minus the integral of v du. So if you choose wisely which one you call dv and which one you call u, you can actually work all that out and derive that. It's a worthwhile skill that you should have just at the point in the semester of Calculus 2, basically, where you're starting to do techniques of integration. So that would be ideal for you to do. If I were to ask you to do that, you would have a table of integrals available to you. Okay, so if that came up on a test, it'd be a table of integrals. However, I do expect you to be able to do the most probable one, which we did by taking the derivative. There's also another one, though. We could do the root mean square velocity, and for that one, it's a little bit more weird. So if we wanted VRMS, we integrate the following. So VRMS is going to be the square root of V bar squared, which is equal to, I'll put a square root out in front. What I'm going to do is I'm going to take the integral from 0 to infinity of V squared f of V dV. And then, of course, I have to divide all that by n. And that's what you have to do. Okay. I'll say ... miracle occurs here equals square root 3 kt over m, which, as I said, is approximately 1.732 square root kt over m. Any questions on that? All right, so that's largely what you have to do for this chapter. It's not too terrible to do those types of problems. We're going to use this over and over for the rest of the semester. Like I said, the next thing your book does is talk about real gases and changes of phase and stuff like that. So definitely want you to read it. So I'm going to say, make sure you read subsection 18-3 very carefully and possibly 2 or 3 times to learn actual science concepts and terms. Always know boldface terms. So whenever you encounter in this textbook, in my class, whenever you encounter a boldface thing like a PV diagram, I'm looking at right now on on section 18.3, that's written in bold print. So I definitely expect you to know that. Liquefation's another one, condensation's another one, diffusion's another one, critical temperature, critical point, all of those things are basically terms that you should know. And in order for you, or the reason why you need to know them is because a lot of the physics of how solids, liquids, and gases behave use those terms. If you don't know what they mean, then you're at a loss. But we're finished now for today. We'll finish off all of chapter 18 next time, and we're right on schedule. Do keep an eye out for my lab and for my YouTube channel. For any extra stuff that I post, I will be posting some more. And of course, you do have your homework assignment was pushed back a little bit since I didn't do as many problems as I wanted to. So hopefully that'll help you as well. I think I'm going to go ahead and move it to where you guys will not have it due until Wednesday. And I think I might have already done that. I'm checking right now. But anybody have any questions? I'll wait for the last person to leave in case anybody does, but you're all free to go.
You said Wednesday as in tomorrow?
What's that, Shanda? Oh, is that Mitchell? Who
Yeah.
said? Okay, what did you say? I'm sorry.
Wednesday as in tomorrow? Tomorrow
Yeah,
night?
I'm looking at it right now. Right now I have chapter 17 is due on the 17th, so that's tomorrow at 11:59 p.m.
Okay.
So yeah, that should be fine. Okay.
Mhm.
If you have any questions on that chapter 17 stuff, send me a text message. It'll be, a little quicker that way. But other than that, if you do send it to me, make sure you send me a photograph of it with the answer choices that you have, if it's a multiple choice type thing, and I'll do what I can to answer it. But you should be good to go. Thanks for coming, everyone.
See you in the morning.
All right. See you, Shauna.
All right.
All right. Who else is here? Sean, did you have a question? All right. Looks like that's it. Have a good one. Bye-bye.